Hello, my name is Kenichi Saikawa. I'm a junior faculty at the Kanagawa University, Japan. Here, I'd like to talk about the Axion dark matter mass prediction from string network simulations. And this talk is based on this paper published in the JCAP last year. In this talk, I basically focus on the QCD, so-called the QCD action. The QCD action is a shared number Goldstone boson associated with the spontaneous breaking of global symmetry, called the Peccei-Quinn symmetry, which is assumed to be spontaneously broken at some energy scale denoted by Fa and called the action decay constant. The QCD action is very well motivated particle because it is originally introduced as a solution to the strong CP problem in QCD and also regarded as a good candidate of the cold dark matter of the universe. One important property of the QCD action is that it acquires a mass due to the non-perturbative effect of the QCD, and the mass is given by this formula, which is very tiny mass and inversely proportional to the symmetry breaking scale. The main question I would like to address in this talk is what is the dark matter, Axion dark matter mass? In the phenomenological point of view, the axion mass or the decay constant is treated as a free parameter of the theory, and currently only the higher mass range or smaller value of the Fa is excluded from astrophysical arguments such as stellar cooling observations. And there are various possibilities that action becomes a dark matter at these broad smaller mass ranges. In this regard, it would be nice if we have some theoretical prediction for the typical mass of the action dark matter, because having such a theoretical prediction would be helpful to interpret the forthcoming experimental results. And we can answer this question by using cosmology. Namely, we expect that the action abundance omega A is given by some function of the action mass, and by requiring that it is equal to the observed cold dark matter abundance, one can invert this relation to have estimate of the action mass. In this sense, the uncertainty in the estimation of the abundance calculation is related to the uncertainty in the action mass prediction. In order to calculate the action relic abundance, one has to fix the assumption about the early universe cosmology. And here I focus on the so-called post-inflationary scenario, where the Peccei-Quinn symmetry is assumed to be broken after inflation. In this case, it is known that the topological defects, such as strings and domain walls, are formed in the early universe. The string is a one-dimensional line-like object, which is formed at the epoch of the Peccei-Quinn phase transition. And afterwards, at the epoch of the QCD phase transitions, the seed-like object called the domain walls are formed and attached to strings. And after that, the system starts to collapse due to the tension of the domain walls. And these objects radiate its energy as the action waves, and it contributes to the production of the dark matter. This is a very complicated process, but if we understand precisely how axions are produced by them, then it should be possible to give a sharp prediction for the dark matter mass. And for such a calculation, we typically have to use some extensive numerical simulation of the axion strings. So here I briefly explain how we simulate the axion strings. So what we are doing is to solve the classical equation motion of the complex scalar field phi in some discretized lattice. And in this setup, the formation of the string is automatically included as a solution of this nonlinear field equation. And this simulation requires a proper resolution of the two different length scales, One is the string core radius, and the other is the hub radius, as schematically shown in this figure. The string core radius is roughly given by the scale mr, which is the mass of the radial direction of this complex color, and inversely proportional to the Peccei-Quinn scale. And one has to take the lattice spacing of the simulation smaller than the string core radius to keep a good resolution of the string core. And Hubble radius, on the other hand, corresponds to the typical distance between two neighboring strings, and one has to take the simulation box sufficiently larger than this Hubble radius. The existence of these two extremely different length scales leads to some difficulty in solving string dynamics. The problem is that string tension, which is energy per unit length, acquires a logarithmically divergent contribution from the action fields surrounding the strings, and it leads to the factor of log of this ratio of these two scales. And the realistic value for this ratio is given by the ratio between the Peccei-Quinn scale to the Hubble parameter at the QCD phase transition, which is a very huge quantity of 10 to 30, and it corresponds to the log parameter of 70. So the realistic case is the string tension is larger by this factor, and it may modify the dynamics of the system. However, it is impossible to reach such a huge hierarchy in simulations with limited dynamical ranges, and one has to perform extrapolation by many orders of magnitude, which is very challenging. Nevertheless, people are trying to estimate the dark matter abundance by performing some numerical simulations. And here I introduce one important quantity for the estimation of the dark matter abundance, which is the instantaneous emission spectrum, and defined by this formula. So this is the time derivative of the energy density spectrum of axion fields, normalized by some factor in order to make this quantity dimensionless. Here R is the scale factor of the universe. And if there's no actual radiation, this factor is a constant and the time derivative vanishes. But there is some radiation of the energy density of axions. It gives some positive contribution. And one can calculate this quantity for each axion co-moving momentum. And one can plot it as a function of momentum, as shown schematically shown in this picture. And typically, this function has two cutoff scales. One is the infrared cutoff given by the Hubble parameter, and ultraviolet cutoff corresponding to the string core scale. And the shape of the spectrum at the intermediate scale may be approximated by a simple power law function, k to minus q. And in this parameterization, the value of the exponent q is important. For instance, if q is greater than 1, the spectrum is sharply peaked at the lowest momentum, and this implies that there are many soft actions are radiated by strings, and correspondingly, there's an enhancement of the dark matter abundance. On the other hand, if q is more than 1, there are also the contribution from the higher momentum actions, and accordingly, the axion number itself is suppressed, and this leads to some suppression of the dark matter abundance. And we want to calculate this kind of spectrum or spectral index in our simulations. So I will outline our strategy in our numerical approach. We calculate the extrapolation in the following way. First, we try to find the attractor or so-called scaling solution of the network, which I will explain in the next slide. And once we find this attractor, we characterize the spectrum of actions on the attractor by introducing some parameters, such as string density parameter or string spectral index. And we measure how these parameters evolve with this logarithmic parameter in the simulation as accurate as possible. here I also introduce some shorthand notation L to represent this log parameter. And then we extrapolate this feature to the large log to give the estimation at a realistic value. We perform such a simulations in the simulation box up to the 11,000 cube lattice, which was possible thanks to the usage of the huge computing resources from Max Planck Computing and Data Facility Garhin, and also some supercomputer from Osaka University. Hereafter, I will present our main result of the simulations. One finding is that the existence of the attractor solution of the system. So in the simulation, we calculated the so-called string density parameter Gzi, defined by this formula. And this roughly represents how many strings exist in the one Hubble volume. And we performed the simulations with different initial string densities and observed how this string density evolved with time. And the result is presented in this figure, where the x-axis is a log parameter, but one can also regard this log as a time variable because the Hubble parameter evolved with time. We can see that from this figure, the different initial conditions appear to converge at the late times, although the convergence is rather slow. What we found is that this kind of behavior can be described by a simple semi-analytical model given by this differential equation of the Gzi parameter. And this model is inspired by this paper where they found that the existence of the perfect scaling solution or equilibrium density configuration when this log parameter is artificially kept constant. And we can expect that the system evolves toward this equilibrium condition such that this time derivative is proportional to the difference from this equilibrium configuration. And we found that this simple model remarkably reproduces this complicated evolution of the system. And even we can find the initial condition closest to the attractor solution, which is shown by this black dashed line. Another important finding is the oscillations in the Axion spectrum. The left panel shows the time evolution of the Axion energy density for each convening Axion wave number. So the different colors correspond to the different Axion momentum. And we see that in the early times, there's a universal behavior, but at the late times, it changes the behavior and starts to oscillate. And we can interpret this behavior as coherent oscillations of the free action field after the horizon entry. So one can show that this oscillation is somewhat expected from as a solution of the free axial field across the horizon crossing. And the existence of such an oscillation would lead to some problem in the calculation of the emission spectrum, because one has to calculate the time derivative of this quantity to calculate the emission spectrum. And for instance, if we calculate this quantity by using the simple finite difference, it typically leads to the lot of contamination on the emission spectrum. And this leads to some systematic error in the estimation of the spectrum. So we developed some analysis methods to filter these oscillating features to extract the overall shape of the spectrum. And we also tried to quantify the systematic error associated with this effect. The third point is the importance of the discretization effects. As I mentioned before, one has to perform the simulation so that the lattice spacing A to be smaller than the size of the string core. And the effect can be parameterized by the quantity MRA, where the smaller value of the MRA corresponds to the simulation with good resolution. The problem is that the physical size of the lattice spacing increases with time, proportional to the scale factor because of the cosmic expansion. So this implies that the resolution of the string core would be getting worse at the end of later time of the simulations. And we actually observed that the spectrum of radiated axions is distorted for a larger value of the MRA. And in such cases, the value of the spectral index is likely to be overestimated. This figure shows the value of the Q measured in our simulations as a function of the log variable. We observe that there is an overall trend that the value of Q is increasing with log, but we also see that this increasing trend is more pronounced at a larger value of log or later times of the simulations. And we interpret these features are due to the caused by the discretization effects. And accordingly, the value of the Q at a larger log is quite uncertain. What we have done is that we introduced a function and performed a global fit. The function is divided to two parts. One is the model function, which models the true evolution of the Q as a function of log. And the second term corresponds to the discretization errors as some function some function of log and MRA. And we choose several ansatz for the model function and perform the fit. And after the fit, we took the limit of the MRA to the 0 corresponding to this continuous limit. The results are shown in these dotted or dashed lines. And different lines correspond to the different choice for the model function. Unfortunately, we found that each different choices of the model function leads to equally good fit to the data. And hence, we cannot say much about the behavior at the larger value of the log. We could interpret this trend as that the Q continues to increase with log linearly. But we could also interpret that this is saturating to some constant value of Q equal 1 at a larger value of log. And the difference between different interpretation is small at log equal 9, but once it's extrapolated to the larger value of log, this difference can lead to some impact on the dark matter abundance estimation. Finally, let me show the result of the extrapolation. The left panel shows the axion produced axion number density normalized by the standard misalignment estimate as a function of the log variable. And different colors represent a different scenario of the extrapolation. And this axion abundance estimation is directly translated to the axion dark matter mass prediction, which is shown in the right panel. Since we don't know which scenario is the correct one, we just take the largest and smallest value of the extrapolated result as the uncertainty in the axion dark matter mass. And we concluded that the axion dark matter mass is predicted in the range of 100 to 450 microelectron volt. So let me summarize my talk. We performed a dedicated analysis of the spectrum of axions radiated from strings by using the large-scale numerical simulations of the Peccei-Quinn field. We found there are several systematic effects that could bias the result, such as initial conditions in the string density, oscillations in the axion spectrum, and discretization effects. From the simulations, we confirmed that there is a trend that the spectral index increases with log, but its behavior at a large log remains uncertain due to the severe discretization effects. And further improvement in the simulation and analysis methods would be helpful to be sure of the extrapolation. So that's all. Thank you for your attention.